Okay, so I would use your caboodle book as your main reference whilst you're revising to make sure you're revising the right stuff, and go through the chapters, look at the key points that are at the bottom right hand side of each double page. So C5, first section, is about the reactivity series, and you should have a knowledge of a list of metals similar to this, okay, and we put them in this order of reactivity based on the chemistry that they do. Right, so some important reactions, first of all with oxygen. So remember that if a metal, I can insert the name of the metal here, lithium, calcium, magnesium, zinc, iron, reacts with oxygen, then we simply describe it as an oxide. If we're going to write them in symbols, remember that oxygen is a diatomic molecule and goes around in pairs. And if I'm reacting it with a metal, so you all know that magnesium reacts with oxygen and makes magnesium oxide. I'm writing the formula correctly here. Okay. Remember that that formula, MgO, is that ratio because magnesium is in group 2. So it makes an ion which is 2+, and oxygen is in group 6, so it makes an ion that is 2-. And when we make the formula, when we write the formula down, we need to make sure that the total charge is going to cancel out and equal 0. 1 magnesium joins to 1 oxygen, because 1 lot of 2+ cancels out 1 lot of 2-. So this is the simplest ratio of magnesium joining to oxygen. Right, but we've remembered that oxygen has to go around in pairs, so if I've got 2 O's here, I can make 2 lots of that, and if I've made 2 lots of that, I'm going to need 2 atoms of magnesium. Okay, so metals react with oxygen to make metal oxides. Remember that the oxygen goes round in a pair, and you might need to adjust any equations if you were balancing some. Some metals react violently and readily, easily with water. Okay? And an example of that is anything in group 1. So if we look up here, we've got group 1 metals, lithium, sodium, potassium. Okay. Calcium does react quite readily with water. It's in group 2. But magnesium is above calcium in group 2. It's slightly less reactive and it only reacts very slowly. So by comparing metals, we can predict what would happen. Let's take sodium as an example. So key facts: if a metal reacts readily with water, we get a hydroxide. And we should remember that anything that ends in hydroxide is going to be an alkali, and they fizz because they give off hydrogen gas. Okay, that's why group 1 are often referred to as the alkali metals. They all react with water to make a hydroxide and hydrogen. Okay, I should put metal there. Okay, so let's change that. I'll put sodium here. So this would be sodium hydroxide plus hydrogen. Again, in symbols, metals are in group 1. Hydroxide ions are 1-. So when the sodium reacts with the hydroxide ion, the simplest ratio is 1 sodium to 1 hydroxide. And we know that we get hydrogen gas, remembering that hydrogen goes round in pairs. And so again, we've got some balancing to do here. We've not got enough hydrogen on this side, so we're going to need to put a 2 here. Okay. If I put a 2 there, to balance up the hydrogen, I need to put a 2 there. If I put a 2 there, I've got to put a 2 there. Okay, so these 2's are necessary because hydrogen goes around in pairs. Most metals either react very slowly with water or only with steam. Remember, steam means hot water in the form of a gas. And some metals will not react with water at all. Okay? If we added oxygen, reaction with oxygen to our table here, we'd see copper and silver react slowly with oxygen, and gold doesn't react with oxygen at all. Gold is the least reactive metal in this list. Okay, we could put platinum down here below it. Okay, that's why gold jewelry stays shiny, because it doesn't react with oxygen at all. Silver stays quite shiny, but it does tarnish eventually over time. Okay, and so people clean their silver. If you've got much silver in your house, they might clean their silver, you know, cutlery, serving dishes, that kind of thing. Okay, so last one, let's look at acids, and that's going to lead us on to talking about salts. So the most reactive metals are dangerous to react with acids because they react explosively. Okay, we wouldn't demonstrate the reaction of potassium and sodium with acid in the lab. Okay, the next most reactive metals, so now we're looking at what? Group 2 and group 3. Calcium, magnesium, group 2. Group 3, aluminium. They react with acids, they fizz, giving off hydrogen gas and forming a salt, which is the next thing we're going to talk about. Okay. Let's write an equation. I need to make a bit of space. Down. Okay. Right, so we're talking about making salts, and we're going to do much more detail about this in a minute. Okay, but our general equation for a metal on its own reacting with dilute acid, remember we'd show that acid was diluted by using this symbol. For most cases, the metals would be solid, and we would make a solution of a salt and hydrogen gas. Okay, when we react a metal with an acid, so you've all reacted magnesium with acid. Magnesium, we choose an acid, yeah, and you should know about 3 different formulas of acids: HCl, hydrochloric, HNO3, nitric, H2SO4, sulfuric. Let's react magnesium with all of these acids. So because the acid is different each time, the name of the salt will be different each time. And we take the name of the metal and the bit of the acid which isn't hydrogen. The name of the metal, the bit of the acid that isn't hydrogen, the name of the metal, the bit of the acid that isn't hydrogen. So the salt will be magnesium chloride. There's our formula. This salt will be magnesium nitrate. And this salt will be magnesium sulfate. I need to put that in brackets. Okay. Now both of these formulas have got 2 of this bit tagged on because the chloride ion is 1-. The nitrate ion is 1-, but the sulfate ion is 2-. That explains why you need 2 H's to go with the SO4 in sulfuric acid. Magnesium is in group 2. It's 2 plus. For every 1 2 plus magnesium ion, I need 2 chloride ions. And I need 2 nitrate ions. But I only need 1 sulfate ion because sulfate is 2 minus. Okay, so don't worry too much about writing formulas, but definitely be able to name the formula, yeah, from the salt produced from any metal with any acid. So if I swapped my metals here, yeah, if I swapped it for iron, I'd get iron chloride. If I swapped it for zinc, I'd get zinc nitrate. If I swapped it for lead very slowly, I would get lead sulfate. And all of these, if it's a metal on its own, produce hydrogen gas. Remember that hydrogen goes around in pairs. I'm going to need 2 of those. I'm going to need 2 of those. I don't need to do anything to this one. Okay, so metals on their own react with oxygen, they react with water, they react with acids to varying degrees, and we use the comparison of those reactions to put together this reactivity series. Okay, second thing about reactions of metals is what's shown in this diagram here, which is called a displacement reaction. Imagine we were trying to write down the word equations for what's happening here. Let's start. We've got magnesium metal being added to copper sulfate, and it's turning into magnesium sulfate and copper. The metals have swapped places. Okay, the magnesium has reacted with the copper sulfate to make magnesium sulfate plus copper. This tells me that magnesium metal is more reactive than copper. Okay, magnesium is above copper in the reactivity series. The magnesium has taken the sulfate away and pushed the copper out, so it's on its own in the solution down here. Okay, the copper has been removed from its sulfate partner. Now we can use this equation to show the fact that what's happened to the ions in this equation. The sulfate has stayed attached to a metal, so it hasn't changed. But the magnesium here, a metal on its own, atoms, has been bonded to the sulfate here, so the magnesium has become an ion. The magnesium atoms have turned into magnesium ions, and they've done that by giving away their 2 outermost electrons. Okay, look at the copper. The opposite is true here. Here, the copper is an ion, and I can tell because it's bonded onto something else. And over here, it's on its own. It's been turned into an atom. The opposite is happening to the copper. The copper ions have turned into copper atoms by getting electrons. So effectively what's happening in here, in these displacement reactions, is a more reactive metal will give up its electrons to a less reactive metal and take its place, displace the least reactive metal from its position in a compound. A more reactive metal can displace a less reactive metal from its compounds. All right? And that's why we refer to these reactions as redox, reduction, oxidation. And remember, Oxidation is loss of electrons and reduction is gain of electrons. So here the copper is gaining, the copper ions are gaining electrons. Okay? The copper ions are reduced to copper atoms, and the magnesium atoms are giving away, they're losing electrons. The magnesium atoms are oxidized to magnesium ions. Right, let's apply that to extraction of metals, because when we find metals in the Earth's crust, unless you're lucky and you find some gold or some silver, yeah, you've got to extract metals from their compounds, and their compounds are usually oxides or sometimes sulfides. Okay, on this side of the diagram here, I've got another representation of the reactivity series, and two important elements have been added that are not metals: carbon and hydrogen. And thinking about our rule about displacement, okay, we're going to apply that to how we can extract these metals. So anything that is below something else is less reactive. So on my diagram here, copper, silver, gold are less reactive than hydrogen. Okay, they're less reactive than hydrogen. If I wanted to extract copper, for example, we could displace copper from its oxide by heating it with hydrogen and making copper metal and water. If I tried to do that with anything above hydrogen, nothing would happen. Nothing would happen. All right? So the least reactive metals could be extracted by heating them with hydrogen. Metals below carbon, so I could go all the way down to the bottom here, anything that's less reactive than carbon can be extracted by heating it with carbon. So a good example would be to take some iron oxide, heat it up with carbon. The carbon will take the place of the iron because the carbon is more reactive than the iron, and the carbon has grabbed the oxygen, and it would actually make CO2. So we'd need two of those and two of those. Okay? So two important facts about the reactivity series. If we include two non-metals in it, carbon and hydrogen, we can explain how we extract metals by displacement. Anything that's above carbon cannot be extracted in that way, and I can only extract these most reactive metals above carbon by using electrolysis, okay, which we're not going to look at now. Right, that's in a different chapter. Okay, so important to understand that we can place other elements into this reactivity series, and the two that we're interested in are carbon and hydrogen. We can extract metals by heating them with carbon as long as they're below carbon in the list, and some metals are less reactive than hydrogen. We can extract them by heating them with hydrogen. Obviously there's far more metals than just these. Yes, Jacob, you will get a periodic table in the test. Okay. There's far more metals than these, and so there's going to be other metals, tungsten, things like that, that are in this reactivity series. So learn the pattern. Okay, learn the pattern, and I would learn my reactivity series. I would try to memorize these metals in like chunks. Yeah, most reactive. Notice there, group 1, 2, and 3. Then we've got metals that are mostly transition metals, okay, and zinc, iron, tin, lead below carbon, copper, silver, gold, platinum, easy to remember, below hydrogen. Okay. So extracting metals, a little bit on applying our knowledge of that. There is definitely going to be a question about writing a method for how you can make a salt from an insoluble oxide or base. Okay, now remember that this term base, the definition of a base are compounds that neutralize acids. And a subset of bases are alkali. Okay? And the special thing about alkalis, the reason they're in a set of their own, remember, is because alkalis are soluble bases. All alkalis are bases, but not all bases are alkalis, because lots of bases are insoluble. Okay? It doesn't mean they don't neutralize the acids, it means they don't dissolve in water, so you can't call them an alkali. You can only give something a pH if it dissolves. We made copper sulfate. Remember making it. Okay? You made a video about how to make the copper sulfate, and it's this process which is in your book. Okay? When you make a salt, be very careful that you're making the salt that you're being asked about. Okay? So if I want to make copper sulfate, which is what this method is about, I need to pick a compound with copper in, and bases are oxides usually, so I'm going to go for copper oxide. And I want to make a sulfate, so I need sulfuric acid. But you won't necessarily be asked about copper oxide. So if I said I wanted to make some copper nitrate, you'd know you'd have to swap your acid for nitric acid. And if I wanted to make some calcium chloride, yeah, you'd know that I'd need to pick a calcium compound to neutralize the acid with. Okay, so be careful, yeah, that your metal and your acid are going to give you the correct salt that you're being asked about. The method would be the same for all of them. Okay, so you can revise this. You must be able to write a good method about this. Okay, remember, you can look at that Focus app on your iPads if you want to remind yourself about the process. There's lots of videos on YouTube about making copper sulfate, free science lessons. Yeah, the required practical, when you see that with an R, yeah, you know that it's a really important practical that you're going to be expected to know the method for. Okay, and I'm saying to you, in your assessment week, you will be asked to write about this sequence of events. Okay, so we want to all be getting 6 marks out of 6 marks. Okay, we all want to be getting the right facts and the right sequence of events and explaining what's happening in each sequence. Okay, so adding the base, copper oxide, to warmed sulfuric acid, stir. Keep adding copper oxide, remember that key point. We want excess copper oxide, and we want excess copper oxide so that we know that the acid has been neutralized. When you can see that there's unreacted copper oxide in your beaker, you know that you've added more than can possibly react, and so all of the acid has reacted, and we can filter the excess copper oxide out, leaving us with the solution of the salt that we want, in this case copper sulfate. And finally, we want to get a dry sample of crystals. Okay, notice that we did this, remember? We evaporated, our apparatus look like this. We're evaporating the salt solution safely and gently over a water bath. The water is going to be evaporating, and we're going to be left behind with crystals of copper sulfate. So we evaporated almost to dryness, and then we leave it on its own to finish off evaporating at room temperature, and you get crystals of solid copper sulfate. Okay, if you're making copper chloride, you get crystals of copper chloride. If you're making calcium nitrate, you get crystals of calcium nitrate. Okay, so make sure a priority that you can reproduce this method. Okay, reproduce the method for making a salt. Okay, and where it says oxide here, right, that applies for any insoluble base, or equally a carbonate. So if I gave you some copper carbonate, you could make salts from it. You could add copper carbonate to sulfuric acid and make copper sulfate and water, but you'd get a lot of fizzing initially because you'd make carbon dioxide as well. Okay, during neutralization, carbonates react with an acid. Let's make some copper chloride and form a salt and water and carbon dioxide, an extra. Okay, so we would end up here with a solution of copper chloride. We'd evaporate it and we'd get pale turquoisey green crystals of copper chloride. All right, really vital. It's definitely on your test. Make sure you've revised this. Finally, let's just talk about the pH scale. So we know that the pH scale shows us how acid or alkali something is. Remember that it's the hydrogen ions and how concentrated they are that tell us how acidic something is. And when we're talking about hydroxides, we're talking about the alkali causing ion, hydroxide. Okay, so on our pH scale, we've got the strongest concentration of hydrogen ions at the lowest number end, and the least number of hydrogen ions at the highest number end. Here we would have an excess of hydroxide ions floating about. Okay, this scale is logarithmic, which you don't need to understand mathematically, but you do need to understand that every time you go up 1, it's a factor of 10. Okay, so it's 10 times weaker each time you go up a number. Okay, 10 times weaker. So if we said, how much stronger is pH 5 than pH 6? pH 5 is 10 times more acid than pH 6, but pH 5 is 10 times less acid than pH 4. And we can multiply that up. So pH 2 is 10, 100, 1,000, 10,000 times more acid than pH 6. Okay, multiplying by 10 each time. Okay, that's an important thing because it means, for example, you can drink lemon juice, it tastes sour, like all acids do. Lemon juice is 10 times less acid than hydrochloric acid, which you wouldn't want to drink. Okay? And we can neutralize acids. We've seen with metals and metal oxides and alkalis and carbonates. So if we were looking at neutralization, we want to react things with acids. We could neutralize an acid with a metal on its own. We can neutralize an acid with a base, a metal oxide. We can neutralize an acid with an alkali, a metal hydroxide. And we can neutralize an acid with a metal carbonate, like limestone. In all of these cases, you're going to get a salt. Always a salt. Always a salt. When it's a metal on its own, we've learned that we get hydrogen. When it's a base or an alkali, we know we get water, which we can evaporate to get our sample of salt. And if it's a carbonate, we get water and we also get carbon dioxide. So those are the general equations for neutralizing acids in 4 different ways. The name of the salt always follows the same rule. Whatever metal you've got and whatever acid you've got determine the name of the salt. So if it's hydrochloric acid, you always get something chloride. If it's nitric acid, you always get something nitrate. And if it's sulfuric acid, you always get something sulfate. And the something is always the name of the metal. Could be the metal on its own, could be the metal in a base. Okay, so we could have magnesium on its own, magnesium as an oxide, magnesium as a hydroxide, magnesium as a carbonate. We would make the same magnesium salt in each case. Okay, so I've whipped through